And in today's episode of Pre-Calculus, we are going to learn how to solve inequalities in one variable. The last lesson we talked about was solving equations in one variable. These are inequalities, basically. You know, greater than, less than, all that shading stuff. Except we're going to do it without shading. We're going to be using intervals to describe our solution sets. We start the notes with a function that is already factored. Yay! We don't have to factor it ourselves. It says to determine the real number values of x that cause our function to be 0, positive, and negative. Okay, well, you know how we do that? Sign diagrams, that's right. Sign diagrams is how we're going to figure out where stuff is positive or negative, or 0. Well, since it's factored, all of our zeros are going to happen when the insides of the parentheses equal 0, right? So let's look at that first set of parentheses. What value of x would make that set of parentheses equal 0? 3. Thank you, somebody. Second set of parentheses says x squared plus 1. What values of x would make that equal 0? Oh, imaginary. Okay, well, those don't count, do they? Because you can't graph imaginary numbers on the real number system plane. Therefore, there are no zeros, there are solutions, but there are no zeros for that second set of parentheses. How about that last one? 4. Yeah, you said it. So the last set of parentheses, x equals 4, would make it equal 0. Going to throw a sign diagram up here. And we're going to check the regions that are created by the numbers 3 and 4. What's happening at the numbers 3 and 4? Polynomials equal 0. Oh, well, we're supposed to be figuring out where it's 0, positive, and negative. We've already figured out where it's 0. That's why they're called zeros. So f of x is 0 when x is 3 and x is 4. And now we just check the regions. Plug in numbers. A really easy number to plug into the parentheses to the left of 3 would be 0, right? So let's see, that first set of parentheses would be 0 minus 3, which is negative. And the second set would be, well, hey, look at that next one. That's x squared plus 1. It doesn't matter what numbers I plug in there. It's always going to be a number that is 1 or bigger. The second set of parentheses will always be positive. And the last set of parentheses is squared. So as long as you don't plug in the number x equals 4, it's also always positive. So if I have a negative times 2 positives, what kind of result do I have? Negative. There we go. All right, well, let's check a number between 3 and 4. Now if we plug in a number between 3 and 4, the first set of parentheses is positive. We've already discussed the second one will always be positive, and the third one, as long as we don't plug in x equals 4, will always be positive. I think it's kind of obvious that that region gives us a positive result. And then lastly, to the right of 4, like the number 5. Positive, middle one's always positive. Last one, since we're not plugging in 4, positive. Okay. Oh, that's green. Or not, should have been green is what I was trying to say. Try one more time. There we are. So f of x is 0 when x is 3 and x is 4. F of x is negative to the left of the number, oh goodness, to the left of the number x equals 3. I can't put a bracket on it because at 3, my function is 0, not negative. And we are positive between 3 and 4, but not including because those are the 2 times where I'm equal to 0. And put it together with all the numbers to the right of 4. Ta-da! Yeah, that kind of stuff's not new, is it? We've done sign diagrams before. We've done quadratic inequalities. That means the only thing we haven't done are polynomial inequalities of higher degree, or scarier stuff. But the point is, you know how to do this already. Look for zeros, right? Put them on a sign diagram. Figure out where we're positive, negative. That means you can easily solve polynomial inequalities of higher degree. You already understand how it's done. Find your zeros, which we'll call critical values. throw them on the sign diagram, check for positive, negative. Pretty easy, right? Pretty darn easy. Oh, goodness. Break my pen. This is a degree 3 polynomial. It has 4 terms. What would be the easiest way to solve it? Grouping would be fantastic if only it worked. So unfortunately, grouping will not work here. So what other methods do we have of factoring this thing? P over Q. We don't know the cubic formula. P over Q. We have to use the P over Q. We have to use the rational root theorem. Oh boy, look at P is the factors of 24. 24 is one of the nightmare situations. You could throw a rock at this number and hit one of its factors. Yeah, 24 is scary. You know what's even worse than 24? 60. 60 is a nightmare. Now, Q is going to be all the factors of the leading coefficient, which is 2. Oh boy. Look at all those options. Let's see. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. 20 options. 20 options. And we have to start testing them using the remainder theorem, don't we? We're supposed to. Could I tell you if you were going, what? No, because a lot of those even numbers you divided by 2, you get one of the other ones I already said. Yeah, the only ones that would be new would be plus or minus 1/2 and plus or minus 3/2. Everything else is already up there. That's why I got the 20. So would you guys be okay? Because you know that you would start testing. You check positive 1, negative 1, positive 2, negative 2, so on and so forth, right? Would you be okay if I gave you one of the zeros and you just know that you would have come across one rather quickly? I'm going to give you one of them. How about I just say, because I'm not going to ask you to do anything this nightmarish on the test, how about I just tell you that 4 is a 0? Save us the time. Tell you that 4 is a 0, but you know you would have used remainder theorem. No, you wouldn't have had to plug every single one of them, because remember, this is a cubic. All you had to do was find one, because once you find one of them and use synthetic division, what you're left with is a quadratic, and you would hope it factors, and if it doesn't, you would solve it by the quadratic formula. Okay, so because it's a cubic, we just need to find one of them, and actually 4 is not the first one that works. To be honest with you, the first one that works is -2, but I don't want to go through that process and find it. 1 for space purposes, 2 for time purposes. We know 4 works because I'm telling you it does. So let's do some synthetic division with the number 4. And we will know that at the end, its remainder will be 4 because of 0 will be 0 because I've told you 4 works. Of course, for the synthetic division, you do have to make sure that your polynomial is not missing any terms. So you see x to the third, 2, 1, none. No terms missing. We're good. So our coefficients are 2, -7, -10, and positive 24. Of course, we start by dropping the 2 down. And we know that we're going to be adding straight down. Awesome. 4 times 2 gives me 8. We'll put it there. Well, -7 plus 8 is 1. 4 times 1, 4. -10 plus 4, -6. And exactly like we expected, we're going to get a 0 here because 4 times -6 is -24, adds straight down to 0. That means what we're left with is the quadratic 2x squared plus x minus 6. And we're trying to figure out where it equals 0. We hope that quadratic factors. If it was going to factor, we would need 2 numbers that multiply to a times c, which is -12, and those 2 numbers need to add to 1. Are there 2 numbers that multiply to -12 and add to 1? Oh, there are? Cool, that means we can factor this, and we'll go ahead and use the Lizzie method for it. At least, or you could use whatever factoring method you prefer. I like the Lizzie method. So we go, okay, I'm looking for two numbers that multiply to this number. A times C is negative 12 because that's 2 times negative 6. And the two numbers that I choose need to add to my B value of positive 1. What are those two numbers again? 4 and negative 3 works just fine. Those do multiply to negative 12. They do add to 1. Yay! There we go. No, those aren't zeros because this is the Lizzie method. You have to remember what makes it the Lizzie method. What makes it the Lizzie method is you put an x in the front of both of your parentheses. And the values you found, 4 and negative 3, get written over your A value, which was 2. This red step right here, this is what makes it the Lizzie method. You would, if you could, reduce the fractions. And of course, the first one does, because 4 divided by 2 is just 2. If I was factoring and not solving, let's be really clear here. If I was factoring and not solving, I wouldn't be able to leave this as x minus 3 halves. I would need to move that 2 in front of the x and get 2x minus 3. But because I'm just trying to solve, I can forego that step because I can see my two solutions now. Those two solutions are x equals negative 2, x equals positive 3 halves, and we already knew, because I told you, that x equals 4. I am running dangerously low on vertical space here, though, aren't I? So I'm going to have to perform some active board magic. Let's see. What? Oh my goodness. Okay, I think active panel's crashing. It is. Awesome. Technology is our friend. Let's try this again. There we go. We're just going to shrink it a little bit. Give myself a little bit more space. Yeah, that'll do. Look at all that space I just found. Magic. Awesome. Because we were actually told to figure out where this polynomial is greater than 0. Shh. That means we need to figure out on our sign diagram where we get positive numbers. So we draw a sign diagram and we put our 3 zeros on it. And those zeros in numeric order are negative 2, positive 3 halves, positive 4. And we do have 4 zones to check. Well, wouldn't it be much, much easier if this was written in factored form? So we have an x plus 2 times an x minus 3 halves times an x minus 4. We're trying to figure out where that's positive. Four zones. If you choose the number negative 3 and you drop negative 3 in, the first set of parentheses is negative, the second set of parentheses is negative, and the third set of parentheses is negative. So if you drop in negative 3, all 3 are negative. What's the result? Negative, because you're multiplying 3 negative numbers. All right, that's not part of the solution set because we're trying to look for the positives. Great number between negative 2 and 3 halves is 0. I love plugging in 0. It's going to give you a positive number times 2 negative numbers. Positive solution. I don't know what that solution will be. I don't care. I know it's positive. 3 halves is 1.5. So we could plug in 2. We could plug in 3. Whatever you're comfortable with. Yeah, 2 is not bad. 2 plus 2 is positive. 2 minus 1.5 is positive. 2 minus 4 is negative. Ooh, 1 negative. Makes the whole thing negative. And then lastly, 5 gives me positive times positive times positive. Yeah, if I plug in a 5, all 3 sets of parentheses are positive. Obviously positive. So our answers, our solutions, because we're trying to figure out where the polynomial is greater than 0, are going to be, so I'll just write solution, between negative 2 and 3 halves, union, everything to the right of the number 4. There you are. That is the answer to that question. Now I want to ask you something real quick. What if, and it doesn't say this, so you don't need to write it. It's just good notes and good thinking. What if it would have said that? How would it have changed my answers? What's up? Where would I have the brackets? Right. So all of the actual rational solutions, -2, 3/2, and 4 would have been brackets if there was an equal to bar, because then I can include those numbers. There's not an equal to bar though, so I can't include them right now. But yeah, that would have been it. Just good to think about. There's a lot going on in that question. Lots of steps. I mean, we're talking rational root theorem, remainder theorem. I cheated, I just told you, but you would have done the remainder theorem. Then there's synthetic division. Then there's factoring. Then there's a sign diagram. I mean, this is a busy question. Got a lot going on. So the next question, can I move? Can I scroll down? No one will panic? Is she still writing? You finished? All right. This one says, this one says solve it graphically. You know what that means? It means you would graph it and ask the graphing calculator where it happens. Can you do that on your test? No? You can't. Moving on. It actually says nope right here on my notes. Yeah, it actually says nope. And the word problems that are all the way in the back of mine also say nope. Yeah, we can graph it without a calculator. It's just a cubic that factors really easily and a linear. And you just would have found all the places where the cubic is underneath the straight line. Would have been very easy to do, but we don't want to. Alrighty, let's see. Solving a polynomial inequality with unusual answers. Wonder what makes these unusual. It says that the inequalities associated with the polynomial function, that means all four. Greater than, equal to. Less than equal to. That's what they mean. The four inequalities associated with this polynomial function have unusual solution sets. Find the four inequality solution sets. I wonder what would make them unusual. I'm just going to rewrite the polynomial up there. We have f of x equals x squared plus 7, that's a quadratic, times 2x squared plus 1, also a quadratic. Well, what are these zeros? What would make the insides equal 0? Nothing. This thing is never 0. Because that first quadratic is x squared, which is guaranteed to be 0 positive, plus 7. So that first set of parentheses is positive definite. That's the word we use in IB. You don't need to know that word. I'm just letting you know. It means it doesn't matter what you plug in. That set of parentheses is always positive. And then the next one is 2x squared, which is always positive or 0, plus 1. So that's also positive definite. That means this fourth degree polynomial exists 100% above the x-axis and never touches the x-axis. That's what makes the solution so interesting. So when is f of x less than 0? Never. We've already said that. So what's the solution? Empty set. Usually like this. Empty set. Yep. It literally means a set that has nothing in it. Empty set. So when would it be less than or equal to 0? Empty set. It's still positive definite. It's never equal to 0 either. What about, ooh, how did I switch to black? I didn't even touch the panel. What about when f of x is greater than 0? When's it greater than 0? Always. All real numbers. So negative infinity to positive infinity? What about when is f of x greater than or equal to 0? Still. No, it's still all real numbers. Because when you say or, if either one of them is true, you're happy. So if I say greater than or equal to 0, well, always greater than or equal to 0. Will it ever be equal to 0? No. No, it won't ever be equal to 0, but who cares? It's an or statement. This infinity is struggling right now. There we go. Okay, part B. Part B, same directions, different function. Part B, same directions, different function. The function this time is a quadratic that is x squared minus 3x plus 3 times 2x plus 5 quantity squared. The first quadratic. Are there two numbers that multiply to be 3 that add to be negative 3? No. First one doesn't factor. Does that mean it has no solutions? It does not mean that. It could have solutions. They might just be complex. That's very loud. So what are we going to do? I'm curious to know, does it have solutions in general? So rather than do the whole quadratic formula, I'm going to just do the part of the quadratic formula that lets me know if it has real solutions. The discriminant, b squared minus 4ac. If b squared minus 4ac is 0 or positive, we have solutions. But if the under the radical part of the quadratic formula is negative, that means we have complex solutions, which means no zeros. Whoa, hold on. People online are trying to talk. What's up? Did you not mean to talk to me? I guess not. Okay. So b squared minus 4ac. This is the discriminant. Our b squared would be negative 3 squared, or 9, minus 4 times 1 times 3. That's negative 3. Guess what? That first quadratic has no solutions. It has no solutions, and the front of the quadratic is a positive number. That means the endings point up, correct? The front of the quadratic is a positive number, so that means it's a smiley. Its endings point up. So we have no solutions and endings point up, which means this quadratic is also positive definite. It does not matter what you plug in, you will get a positive result. But what about that next set of parentheses? It is squared. So is it positive definite? Jenna, you said no. Why? Oh, I don't know. Oh, you don't know. She's just saying no. Okay. Someone who said no, why would you say no? What do you think? You mean y equals 0? Yes. This function has a 0 at x equals negative 5 halves. So what does that tell you? That tells you that this thing is greater than or equal to 0 everywhere. It's equal to 0 at negative 5 halves. So if I said, where is f of x a negative number? Well, excuse me, g. I'm sorry, not f, g of x. My apologies. Just so used to writing f of x. There we go. So when is it negative? Never. It's never negative because it's a positive definite quadratic times something that is always positive or 0. So you can, what's that? You don't. I mean, like, not in this one. You need some things that are not positive definite. So where is g of x less than or equal to 0? At 5 halves, negative 5 halves. At the point x equals negative 5 halves, it does equal 0. See, I didn't say it has to be less than 0 and negative. I mean, less than 0 and equal to 0. No, I said or. So if either one of them is satisfied, answers. And since we have a 0 at negative 5 halves, it's a solution there. So where is g of x strictly positive? Hold on. Where is it strictly positive? Chris? Everywhere except for negative 5 halves. So how do I write this? Negative infinity, I'm trying to squeeze it in here. I don't know if it's going to fit. Negative 5/2. I'm going to run out of vertical space. I mean horizontal space. Oh my gosh, it's terrible. Let's see if I can. See if I can isolate just this stuff. Nope, of course not. Oh well. I'll just have to string it together over here. Union. Sorry, I'm out of space. Negative 5/2, comma, positive infinity. And then lastly, where is this polynomial greater than or equal to 0? I said or, greater than or equal to 0. Everywhere. Because it's equal to 0 at negative 5/2, we can now include it. Yes?
So like there's a cool symbol for the set that contains nothing. Is there a cool symbol for a set that contains everything?
If it contains everything, so if it contains all real numbers, then you just use this. That symbol represents all real numbers. But I won't be using it. I'll be asking you to use negative infinity to positive infinity. But in set notation, that's what you would use. Actually, what you would use, you would say the set of x's such that x is an element of the real numbers. That's what that says. That's all set notation. That says the set of solutions x's such that x's are element of the real numbers. That means x could be. It means negative infinity to positive infinity. That's just it in set notation. Don't worry, you don't have to know set notation for this course. Yeah. You don't need the set notation stuff. You can ignore that. What's that? Yeah, I'm sorry I ran out of horizontal space on my union over there. It's terrible. So, Trey, you said you refined your question. Completely lost it. I think I've completely lost it. Ready? All right. Create a sign diagram for the rational function. Oh, cool. So we've been working on rational functions, haven't we? Oh, now he remembers this question. Yeah, what's up? Because if you say if x equals negative 5/2, that's where the polynomial is equal to 0. So if you say greater than or equal to 0, it satisfies one of the two conditions, and as long as it satisfies one of them, it satisfies.
How would anything? Oh, what stops it from being less than?
Nothing. It does. It's less than or equal to 0 is part of the solution too. Negative 5/2. It's right there. You know what? Here, I've got a moment. Tell you what. Let's do this. Oh, let me put it on Desmos so you can see what we're doing. Okay? Yes. So why are they both empty set? Because this one's never equal to 0. Never equal to 0. Yeah. So Trey, yes, Desmos or no? Huh? Will help. Okay. I'm not going to be able to read the polynomial anymore once we're there, so I'm going to need your help. Everything's running very slowly because I'm trying to stream technically over Zoom and record at the same time. Okay, so what is it's x squared. Hold on, minus 3x plus 3, and then, whoops. And then in this one is 2 minus 5x. What is it? 2x plus 5 quantity squared. Okay, check it out. This is the entire function. I mean, it does some wackiness up here, you see, right? So does it ever exist below the x-axis? No, I know, no, so never, right? So is it ever below the x-axis or on the x-axis? Yes, at one place, at negative 5/2. So because it satisfies one of the two conditions, because it's an or statement, It is part of the answers. That's what's nice about ORs. They don't have to both be true, just one of them. Both true is an and statement. Or statements goes, yo, as long as one of the things happens, we're happy. Like right now. No, never mind, I'm being recorded. Don't want to say anything inappropriate. All right, so we're going to close Desmos, leave. And let's go do this sign diagram for this rational equation. Now, we've been working on rational equations for a couple lessons now, right? Psst. Time for me to let you in on a little secret. Sign diagrams have to have more than just the zeros on them. There is a reason why we practiced finding zeros and finding, what are those things called? Asymptotes, discontinuities. Because not only do zeros belong in our sign diagrams, but so do our discontinuities. So deleted points would have to be on sign diagrams, vertical asymptotes have to be on sign diagrams, not horizontals, because the sign diagram represents our x-axis. So yeah, sign diagrams need zeros and discontinuities. Well, how do we find the zeros? Do you guys remember? How do we find zeros? Is the bottom allowed to be 0? No. So for zeros, you guys are killing me. The top has to be greater than 0. I mean equal to 0, not greater than 0. You find, look, it's a fraction, right? What is the only time the fraction has a value of 0? If the top equals 0. So where does the top of this thing equal 0? Negative 1/2. Discontinuities. Well, how do we find them? Yes, when the bottom equals 0, because you are not allowed to divide by 0. This is going to happen at 2 places. This is going to happen when x equals -3 and when x equals +1. You see, this rational function was already factored for us. Whew, thank goodness. Well, the question says determine the real number values that cause this rational function to be 0 and undefined. Boom, we got it. We got all 3 critical values. Make a sign diagram so we can determine where this thing is positive and negative. So sign diagram, 3 values on it. -3, -1/2, +1, 4 zones. But every time you've seen me put a critical value on a sign diagram, it was a 0, right? So just looking at this sign diagram, it would appear as though I have 3 zeros, but I don't. So the sign diagrams show you that it's a discontinuity like that. What looks like a tiny little vertical asymptote. That shows us those are discontinuities. And then we get to check our zones for positive and negative. Oh, a bunch of hands went up. Okay, I must have done something wrong. Paxton? Yeah, just -1/2. Yeah, thank you. Ladies, was that what it was? Sorry, I just forgot the over 2. Okay, at least it wasn't a colossal boo-boo. You don't have to erase anything. Whew, that's good. Let's check zones. To the left of -3, like -4. If we plug in a -4 to the top, we get a negative number. And if we plug in -4 to the bottom, we get a negative number times a negative number. That's 3 negatives. So is the value going to be positive or negative? Negative. Remember, an odd number of negative signs makes a negative. Let's see, what's between -3 and -1/2? How about -2? That one's pretty easy. -2 on the top would give me a -3, so a negative number. And let's see, -2 on the bottom is going to give me a positive times a negative. Positive because it has 2 negative signs. My favorite number to test, 0. See, it's going to give me a positive on top. And on the bottom, I'm going to get positive times negative. Crud. Negative. And then lastly, anything bigger than 1, like 2. Looks to me like it's going to be positive over positive times positive. Boom. Now, I'm actually going to do more than the question asked for because I think it's good mathematics. So let's figure it out, not only where it's positive and negative, but where it's also greater than or equal to, less than or equal to. What do you think? Can we do that? Because it seemed like that was kind of a struggle. So where is it r of x? So where is r of x? It says positive first, so I'll say greater than 0. Well, that answer is just going to be everywhere where the sign diagram showed us positive. So from -3 to -1/2, strung together with everything to the right of the number 1. It's not bad, right? So how does this change if I throw an equal to bar on there? Greater than or equal to 0. You put a bracket on the -1/2, and that will be the only thing that changes. You can't bracket a discontinuity. And -3 is a discontinuity. Holy cow, that was loud. Then we can check for when our rational function is negative using the sign diagram. Negative to the left of -3. Strung together with all the things between -1/2 and +1. Now again, the numbers -3 and +1 are discontinuities. So if I throw the equal to bar on that less than symbol, once again, the only thing that will change is bracket on the -1/2. Oops. Can never bracket a discontinuity. Come on, panel. Come on. There we go. Boom. There it is. And because that's where I stopped in period 1, that is going to be where I stop in period 8 as well. Yay!